Okay, good evening, everybody. So, let us start our lecture today, and then let us see our schedule first. We are almost at the end of this semester in the course. So this week we will discuss dynamic programming, actually a new another concept of programming. So this is in chapter 15 in the book. Okay, the book in chapter 15. Okay.
Can you take the attendance now?
Later. You wanna leave?
Oh, I can't do the full lecture.
Okay,
I was at the.
I will give you attendance, no problem. Whatever you, how long you can stay is good. Whatever you can do, no problem. I'll remember you. Or maybe I may not count attendance for tonight. Okay. So dynamic programming is a new approach of programming, like divide and conquer method. Okay, we solve problem by combining solution of subproblem. Actually, if the problems are not independent. Okay, so if there are some characteristics that the requirement that dynamic programming is applicable only if the problem can be divided into some subproblems, and the subproblems are not independent, like some dependent subproblems. Like for instance, we are familiar with recursive method, right? So you're familiar with recursive method. So like recursive method, for instance, or divide and conquer method, you're familiar with divide and conquer method. So in divide and conquer method, there are 3 steps, we know that, right? So we break down the problem into some independent subproblems, and then solve the subproblems recursively and combine the solution. Okay, and then we get the solution of the original problem. So in dynamic programming, okay, so actually that's almost similar concept. Okay, so but the dynamic programming is applicable when subprograms are not independent. In divide and conquer method, you see that we used, okay, so we do partition into independent subproblems. For instance, in a list, in divide and conquer method, we made 2 independent lists, left portion or right portion, something like this. Okay, so there's no relation between these 2 links, between these 2 sub list or sub problem that we want to sort it or something or search. Okay, but in dynamic programming is applicable only when the subproblems are not independent. That means there are some dependency or relation. Okay, for instance, we are familiar with some this kind of dependent subproblems. Those are mostly that we solve either sequentially or recursive way. For instance, let us consider some recursive methods. For instance, finding factorial of a number, okay, or finding Fibonacci series, or finding combinations. Combination, actually, this is the formula for the combination. Okay, so we say in books, some books we have, maybe in mathematics. Give me a second. In mathematics, you are familiar with this kind of symbol. For instance, NCR equal to factorial of n divided by factorial of r into factorial of n minus r, or something we can write, like for instance, we can write equal to factorial of n. So if you use this symbol, it's easy for computer typing, but do not forget about the dot exclamation sign actually. Then factorial of r into factorial of actually n minus r, n minus r. Okay, so that's actually ncr equal to this. So you should, if you took mathematics course, you should be familiar with this combination. So similarly, there are some some determination, like for instance ncr, for instance factorial of n equal to n into factorial of n minus 1 equal to n into n minus 1 into factorial of n minus 2. You are familiar with this, right? Similarly, there is another derivation is that in c, we can say k or r, whatever you say, equal to n minus 1 c of k plus n minus 1 c of k minus 1. You may be familiar with this. Okay, so this kind of, for instance, now see that there is a relation. So this is a main problem, and we can divide this problem into some similar problem. Okay, some similar problem. Similar, we say not independent, that means dependent. Okay, that means this part is this k and n are dependent with this k and n. They're related. Okay, not independent. Okay, so for these kind of problems, solving this kind of problem, it is useful to use dynamic programming. Okay, we will see that for dynamic programming, programming concept have some efficiency, better efficiency. Okay, we will go through this some example, and then let us see a few more example. For instance, for this one, we said okay, actually the lines are broken. Lines are should be like this. Let me make it larger. Okay, so we have this formula, right? So we know this formula we have in hand. So NC, that this is this like this, NCK equal to n minus 1 c k minus 1 plus n minus 1 c k. So in programming, whenever we write, for instance, a method or function, so we cannot write with suffix and prefix and suffix way, right? So we can write, for instance, here c, okay, c or whatever method name you get, combination or c of n comma k equal to c of n minus 1. Sorry. C of n comma k equal to c of n minus 1 comma k minus 1 plus c of n minus 1 comma k. Like this is how we pass argument parameter to a function, right? So the function name we can say com or com c, whatever we say. Okay, for simplicity, I use this. Okay, so for instance, so we wanna find out C of like 6C4. Okay, so according to this formula, this formula, this split, okay, splitting formula, we say that it's equal to 5C, okay, you can say K minus 1, that is 4 minus 1, 3, plus 5C, okay, here is K, 5C4. So this is why 5C4 over here, and this is that one, and this is this one. Okay, so come 5C3. Okay, so it comes, so whatever function name you give, 6,4 equal to 5,3 plus 5,4, and then again you split this using same formula, equal to 4,3 4,2 plus 4,3, and then you do this, you get this 3,1 3,2, and then so the formula, now we know that the basis we have NC, okay, NC1 equal to factorial of n divided by factorial of 1 into factorial of n minus 1, right? So equal to, whatever say, n into factorial n minus 1 equal to n, actually equal to n, okay? This is why. So then whenever we recess to 1 over here, so then we can get a 3 over here. And for this one, we do again, split again. So come 2 1, come 2 2, and then we know that come 2 2, C of 2 1 equal to 2. So this is the base level. Okay, these are the base level. These are base level. This is base level. Okay, and then this is base level. This is, and there is another formula, actually there is another one, NCN equal to factorial of n divided by factorial of n into factorial of n minus n. So we know that factorial of n cross out, factorial of 1 by factorial of 0, factorial of 0 equal to 1, right? So equal to 1. So here this is another base, so this is base 1, okay, this is base 1, this is base 1, okay, and this is base 1, and other stuffs, this is base 1, okay, this is base 1, so this is base 1, okay. So our base is, for instance, this one, actually NC1 and NCN, right? So for instance, while using a recursive method, a function, a recursion are called like this way. Okay, so if you, okay, does anyone has any question about this?
Yeah. How are they not independent? So like, is n minus 1 and k minus 1 and n minus 1 choose k? Are those the two things that should be dependent on each other?
Dependent, that means, for instance, this n is this n. This n is this n. K is this k. This k is this k. I'm saying this one.
So wouldn't the n minus 1 choose k minus 1 be like the first sub problem, and then the n minus 1 choose k be the second sub problem?
Yes.
Okay, so those should be dependent on each other?
No. They, so that the entire thing, the entire this part is dependent. So we are, so this sub problem is dependent. For instance, this part is like similar. This part is similar.
Oh, so the sub problem is dependent on the whole problem.
Yes, sub problems are related. For instance, how do we use, recall the recursive method? Okay, let me go a simple example one. For instance, on factorial of a number. Recall that factorial, how factorial of a number is. So please mute yourself. Okay, like factorial of a number. How factorial of a number is derived? X equal to, for instance, x equal to 5. Factorial of 5 equal to 5 into factorial of 5 minus 1, 4, right? And then factorial of 4 equal to 4 times factorial of 3. So this part is similar, right? All of this derivation are similar, right? This is why there is a similarity. This is why we can apply recursive method, right? If there is no relation, then we cannot apply any recursive method, right? Remember that the condition of using recursive method is that the function can be split into similar subproblem, right?
Yeah.
So that a function can we are discussing maybe. So in the book, okay, the book has this one. Yeah, please mute yourself. So the book has this formula. It has the proof. The book has some proof. But it is a mathematical, actually, an expression. You can do Google search, or if you take mathematics course, you may learn how to prove this. So our goal is not to prove this one, okay? Our goal is to see how actually this is called, okay, finally what it happens. Finally, what happens that this result are added, right? So combination of 4, 2 is added by this, right? So, and this is find this plus this. Okay, so that means this will be 3. So this is 3, and this will be 2 plus 1, 2 plus 1, then 2 plus 1 will be 3. That 3 plus 3 will be 6. Okay, and this part is 2 and then 1, then 2 and then 1, then when we add up, then 3, right? We can prove sum. You say that factorial of 3c1 equal to 3, factorial combination of 3c2 equal to 3. Okay, and then this part will be 1, so this part will be 3 plus 1 equal to 4. Similar, this part is 2, this part is 1, then 2, 1, this part is 3, this part is 1, then 3 plus 1 equal to 4, and this part is 1, 4 plus 1 equal to 5, and this part is 6 plus 4 equal to 10, and this part is 10 plus 5 equal to 15. Let us do this. Okay, let us do this, whether it is 15 or not. Let us check it. Okay, so 6c4 equal to factorial of 6 divided by factorial of 4 times factorial of 6 minus 4 factorial of 2. Okay, equal to 6 into 5 into factorial of 4, and in the down factorial of 4 times 2. Then factorial of 4 is gone, and then 30 divided by 2 equal to 15. So we got 15. The result is correct. So this approach is a bottom-up approach. You see that the bottom-up approach, the results are combined from bottom to up. So this is a bottom-up approach. Okay, So in the bottom-up approach, something that have you realized that how many times we are using, for instance, this one. You see that some methods we are using multiple times. For instance, this one. We are using this one this time over here, and then calculating this one over here, again this one over here. Okay, 3 times, right? Similarly, comp 3 2, we are counting over here. Similarly, we are counting over here. We are calculating over here. Okay, and we are calculating same process multiple times. So that means it will take more time, right? So the same method is being executed or splitting multiple times. But how about if we do not do it? How about if we can store the value of combination 3.2 at some place and reuse that value instead of calling this again and again, okay, to the base level until the base level. How about if we save this value in another place, for instance, in an array or in another variable, and we can reuse this? Then our program will be shorter, more efficient, right? Do you understand the efficiency? I'm telling that you see that we are calling some again and again and again. So in the dynamic programming, it will be our goal. So what we can do, what we want to do, instead of calling some methods, okay, again and again. You know, for instance, we are only finding combination of 6 4. How about if we want to find combination of 60 40? There will be huge call, right? There will be huge call, right? It will take, so in the recursive way, this is a recursive way, it will take a long time. Okay, so our goal will be not to call the methods that is being executed one time. For instance, at some point, whenever we reach combination of 6 4, we know that value is 15, okay, by one time calculation, and then later we do not want to do same calculation. Okay, this is the concept of dynamic programming. Okay, so let me show you another example. So the book has this one. Okay, it's appendix C, counting and probability, appendix over here. So now let us see a simple one, for instance. Okay, how do we find Fibonacci number? We know that Fibonacci series is something like this, right? So Fibonacci series is, okay, does anyone has any question about this one before I move? Okay, please give attention here. Okay, so please give attention here. So we know the Fibonacci series is like this, right? 0 1, and every third number is the sum of the previous two numbers. Okay, 0 plus 1 equal to 1, 1 plus 1 2, 1 plus 2 3, 2 plus 3 5, 3 plus 5 8, 5 plus 8 13, 8 plus 13 21. Okay, and so on. Okay, so this is a recursive method. It's a recursive Fibonacci number. Do you remember that this is a recursive method? How do we implement it? This is the factorial, is mathematical definition of Fibonacci series. 0 if n equal to 0, okay, or 1 if n equal to 1. So these two are base, and then otherwise equal to if n greater or equal to 2, then Fibo of n minus 2 plus Fibo n minus 1. That is the previous number. Okay, if n equal to 2, then Fibo of 2 minus 2 equal to 0, then 0 equal to 0, Fibo 0 equal to 0, okay, plus 1, Fibo 1, 0 plus 1 equal to 1. So then whenever we got the third number, then fourth number will be this plus this. So this is the mathematical definition of Fibonacci series. And in the Fibonacci series, this is the recursive implementation, right? Recursive implementation. Fibonacci series. Fibonacci series. So does anyone has any question about this one? Now let us see how this Fibonacci, this one, okay, how this Fibonacci, this method is called. Okay, so for instance, if we want to find the fifth Fibonacci number, give attention please. This one is simple, maybe it will be easy for you to understand. If you did not understand the previous one, it will be easy. How do we find the Fibonacci of 5? So our formula is Fibo n equal to, remember that, 0 if n equal to n, if n less or equal to 1. Okay, otherwise Fibo n minus 2 plus Fibo n minus 1. This is the Fibonacci formula, right? So if you want to find Fibonacci 5, Fibo of 5 equal to, then Fibo of 5 minus 3, 5 minus 2, 3, Fibo of 3 plus Fibo of 5 minus 1, Fibo of 4. And then Fibo of 3 equal to Fibo of 1 plus Fibo of 2. Okay, we can say plus. Okay, so you can say plus. You can give plus sign over here, no problem. Okay, and then Fibo 2 equal to Fibo 0 plus Fibo 1. And you see that here Fibo 4 equal to Fibo 2 plus Fibo 3. And then Fibo 3 equal to Fibo 1 plus Fibo 2. And then how many times we are calculating Fibo 2 over here? 1 time, there's 2 times, so there's 3 times. Okay, so in the recursive method, this is a recursive method. Using the recursive method, we are calculating, we are doing some redundant work, right? Here we are doing same thing. Okay, again and again. So for instance, this 3 part, this Fibonacci 2 is being calculated 3 times. So but how about if we, so in a dynamic programming, actually our goal will be not to calculate Fibonacci 2 3 times, only 1 time. Wherever we reach first, for instance, wherever if we reach this one first, and we will use that value over here. We will not do this part. We will not do this part. If we know that Fibonacci 0 equal to 0, Fibonacci 1 equal to 1, so Fibonacci 2 will be 0 plus 1 equal to 1. And then instead of calculating this one, we will just put 2 over here, so 1 over here, Fibonacci 2 equal to 1. Okay, and Fibonacci 2 equal to 1, Fibonacci 1 equal to 1, then Fibonacci 3 will be 1 plus 1, 2, and then Fibonacci 4 will be 2 plus 1, 3, the fourth number, 0, 1, 2, 3, 4, fourth number is 3, and Fibonacci 3 will be 2, then Fibonacci fifth Fibonacci number equal to 2 plus 3 equal to 5, so fifth Fibonacci number equal to 5. This is the fifth Fibonacci number. 0th, 1, 2, 3rd, 4th, and fifth Fibonacci number is 5. Okay, so this calculation apparently it looks like simple, okay, but this is a bottom-up approach. So what we do, we know that whenever we do recursive call, we use stack, right? So that this is 1, this value are again 1 plus 1 equal to 2. So the values are going from bottom to up, right? And stack is being used to do this calculation. Okay, and you see that there are redundant code over here. Okay, and then time complexity of this will be exponential. Okay. So the time comes here. So you see that it is calling being one time. So let us do this showing. This time calculation will be b go up 2 to the power n. Let me show you briefly how do we get this time complexity. But before I go here, does anyone has any question about this one? Why do I say this is bottom up? This is a bottom up approach. You understand? And maybe I will show you how do I find this complexity actually using divide and conquer method. Okay, this is here for instance. So let me show you. So the formula is over here. Tn equal to Tm equal to 2Tn minus 1 plus 1, right? So why we need to, this is why in the base case, okay, I will show you that why we need to do this. For instance, let me go back in the code. If you go back in the code, right? So how many times we are calling this code? So over here, it is one time, right? We're calling over here one time. And over here, we are calling n minus 2 and n minus 1, right? This is pretty here tn minus 1. So the actually pretty n minus 1 plus tn minus 1, then plus 1, and this is plus 1. So the actual total time equal to tn equal to 2t n minus 1. This is plus actually 2. So whatever value is 2 is constant. Okay, whatever value is 2, 1 or 2, whatever we say, you can say 1. Okay, this is actually for large n, for very large n. If n is very large number, so then there is no difference between n and n minus 1 and n minus 2 minus 1. Okay, so that means we can write equal to 2t n minus 1 plus 1. Okay, this is actually 2t n minus 1. Okay. Okay, so this is the time complexity equal to 2t n minus 1 plus 1. So you see that how this recursion is called. How this recursion is called is, if you remember that, for if we do split, okay, for instance, this is tn time complexity, tn equal to, this will be 1, okay, 1 plus this one, actually this one. So we are considering for large n, okay. Time complexity is calculated for large n. So tn equal to 1 plus 2tn minus 1, tn minus 1 plus tn minus 1. Okay, so then again this tn minus 1 is being calculated 1 plus tn n minus 2 plus n minus 2, right? So if you replace n by n minus 1, that will happen. Tn minus 1 will be, that means t of n minus 1 equal to 2t n minus 2 plus 1. This is over here 1, then t n minus 2 n minus 2. And this process will continue for some time. And at the end, all the way in, it will reach to 0 time, t0. Okay, for instance, it will reach in the base case, right? In the base case, t, if it is 0, then n equal to 0, then 0. And then how many times we are being calculated? This is being called one time, that means 2 to the power 0. This is being called, these are being called 2 times, that means 2 to the power 1. This is being called 4 times. For this one, we are getting this time, and there is another part over here, similar part. This similar part over here, so we did not show this over here. That has another 2, so the 2 to the 2 plus 2, 4. That means 2 to the power 2. Okay, and ultimately, like this way, it will be going to, for instance, k. If their length is k, if the length is k, okay, so then this will be going to 1 plus 2 plus 2 squared plus 2 3 plus 2 dot dot 2 to the power k dot dot, there's a dot dot plus 2 to the power k. So this is a geometric expression. The sum of this expression equal to 2 to the power k minus k plus 1 minus 1. This is mathematical. And then time complexity will be big O 2 to the power k. And for large k, when k, if k greater than close to n, then equal to 2 to the power n, equal to big O 2 to the power n.
Since this is a recurrence, couldn't we have just used the master theorem?
Yes. So in the master theorem in the book, you see that there are some. Let me show you. Give me 1 second, please. 2 to the power n. In the book, you skip some complex stuff. In the book, if we go chapter 4, right? Chapter 4, divide and conquer method, we discuss some simple stuffs. Where is the master theorem? Let me go very close. So this one, you see, like this one, similar this kind, divide and conquer method, like this. Okay, this is for logarithm in n square, but that one we got 2 to the power n, like this. So this is our problem, for instance, here. Okay, so you can get the solution Tn equal to 2Tn plus 1 plus 1. If you find the solution of this one, you will see that this it takes is this one. Is exactly this one what we are discussing, equal to big O 2 to the power n. Use recursion tree to determine a good asymptotic upper bound on the recursion. This one, you see that we did not discuss this, but this is a mathematical actually. This when I was an undergraduate student in mathematics, then I remember that I will solve some of this kind of problem. Okay. So then, Cameron, what was your question then here? You understand how we get big O 2 to the power n? So this is an exponential, right? So for for finding a small number, like for instance nth Fibonacci number, for instance 5th Fibonacci number or 6, 7, 8, 10 Fibonacci number, it is simple. But finding a large Fibonacci number, this 2 to the power n, for instance, if n equal to 100, okay, or 1000, this will be very time consuming, right?
Yes.
Okay, so now our goal is to use dynamic programming. So the dynamic programming concept, for instance, we want, okay, in dynamic programming there is a concept. It's called memoization. It's not memorization, memoization or something. Okay, we will find that term over. So the concept is that, let me tell you the concept, then if you understand the concept, it will be easy for you to go. Okay, so And this same Fibonacci number, now we want to implement using dynamic programming concept. Okay, then how do we do this? Okay, then let us, instead of recursion, let us use another array. Okay, declare an array, and it is a type array. For instance, the array is f. My array over here f. And initially, for instance, if whenever you declare an array, so we know that in some programming languages we put some default value. Maybe put the default value that is not our expected value. So we know that in a Fibonacci series there is no negative number. So initially we can put all -1, -1, -1, -1. Whenever you declare an array, put -1. Otherwise, if you even declare an array, do not declare, then all value will be put 0, right? By default, some programming languages like Java put 0 for an uninitialized variable. So whatever you put 0 or 1, 0 or -1, that is not a matter. So for instance, we use an extra array over here. Now we want to implement this. Okay, the function, for instance, that we are declaring this an array. Okay, this is an array we are declaring. Now what we are doing, so instead of see that code is almost same, but here we are declaring that initially, okay, we are putting f0 equal to 0. So then initially what we'll put f0 equal to 0 and f1 equal to 1. These are our base case. Okay, this is the index. These are the index 0, 1, 2, maybe 4, 5, 6, maybe 7, and so on. Okay, and simply we can declare an array of size n plus 1, whatever my n Fibonacci number, n or n plus 1, we can declare an array. 2n, whatever is said. You do not take that much memory. Now for integer n from 2 and upward. Okay, what do we do? So that we say that whenever we put this one, initialize this one 0 and this one 1, and then for 2 and upward, from starting from here, 2 index 2. Okay, if fi equal to fi minus 2 plus fi minus 1, that means if this one fi, these are I. Okay, initially I equal to 2, I equal to 2 over here, this is I. Okay, this is I. So when I equal to 2, then what we say, if I, that means f2 equal to if I minus 2. What is I minus 2? I equal to 2, I minus 2 equal to 0. Plus f of I minus 1. What is I minus 1? 2 minus 1, 1. That means this will be 0 plus 1 equal to 1. And for 3, now I will go over here. I will give 3 over here. 3 for I3 equal to f of 3 will be f of 3 minus 1, 3 minus 2, that is f of 1 plus f of 2. Okay, that is this one plus this one. 1 plus 1 equal to 2. And similarly for 4, 4 will be f of 4 will be f of 2 plus f of 3. Okay, then 1 plus 2 equal to 3. And then 5 will be 2 plus 3 at 5. And then here will be 3 plus 5, 8, and so on. You see that program is very simple, only a little bit change, right? Previously, what we are doing over here in a recursive way, we are recursively what we are doing over here. We are saying that return Fibo n minus 1 plus Fibo n plus n minus 2. We are doing like this. Previously, what we did previously, we did Fibo n minus 2 plus Fibo n minus 1, right? Instead of doing call, this is recursive call. Instead of recursive call, there is no recursive call over here. What we are doing, we are using an array and we are updating the array based on the index value. Okay, and one returning if n, whatever n is provided over here. Then this program is very simple. And how many times these are being executed? Let us see. So there is only one for loop, right? So the time complexity will be big O n. Here there is only one for loop. So this part will be 1, right? This constant part, this time this part will be executed 1. This part is constant. Okay, this part is constant. Only there is a for loop over here, and this is simple for loop. So the complexity will be big O n. And compare, and previously the complexity was big O 2 to the power n. So 2 to the power n is very greater than big O of n. That is less than 2 to the power big O 2 to the power n. So which one is efficient? This one or the recursive one? Cameron?
This one.
This one, right? So we see that dynamic programming actually, so it is efficient. But what the dynamic programming is as at the beginning we saw that it needs to be splittable into some non-independent. Okay, that means some kind of dependent parts, subproblems. The main problem, what is our main problem over here? Finding Fibonacci of a number. Nth Fibonacci number, for instance, 5th Fibonacci number, 6th Fibonacci number, whatever number we want to find. And then what we are doing, we are we split the problem, and then you see that problem are solved easily. So instead of having a an exponential method, we got a linear method, right?
Is it top down?
Yeah, this is top down. Top down, that means it's coming. It is top down, or we say left. If we declare this array, it's left to right, left to right. So top down methods are sometimes called left to right because we are starting from the array index 0, array index of 0 and 1, and we are going. So if you declare this array like this, a good question though. If you declare this array, I would declare this array like this. Okay, maybe you would understand easily, right? If 1, 2, 3, 4, 5, 6, 0, 1, 1, 2, 3, 5, 8. So if I would declare this array if like this, you understand, right? This is a top to down, right? Top down approach. Okay, because the previous values, if there is no stack used, we don't need to use any stack for this one, right? This program does not use any stack, but we know that all recursion method they use stack. Does anyone has any question? Okay, I want to give you homework, very simple homework. So write a program in Replit. Okay, and in the same program, okay, do implement Fibonacci both in 3 ways. One is linearly using a for loop, or at least, okay, Fibonacci is like this one, maybe 2 ways. Okay, using a 2 ways, using a recursive method and using dynamic method like this. Okay, and compare and call this method for a large n, for instance, any number 20, and compare the time required to execute both methods. So you can do a Google search to find the timestamp, to how to find timestamp. Okay, timer to get the time before starting an expression and end after ending an expression, how much time it takes. If you do Google search, there are some many courses that you can use. So then you will see that there will be difference in timing, huge difference in timing. Practice this one, okay? Does anyone has any question?
Yes. So is the reason that they're dependent on each other is because they use the same part over again, like that you stored in an array?
We not necessarily we are storing it. We are finding the dependency here.
Because they both share that array, and that's why they're dependent on each other?
Problem is similar. We are calling that problem is similar. Like for instance, like recursion. Okay, let me give an example. Okay, so if you want to, for instance, if you want to find a, forget about this Fibonacci series. Okay, so if you are given the number like this, okay, if you want to do a binary search algorithm,
Checking Martin's trees would also be as well.
right? You know that
It's true. I believe doesn't work.
starting index and the left index, right index, and the middle index. And then whenever you get index, then you can find the starting value, last value, and mid value. Compared to the mid value, for instance, if you do search whether the number 2 exists or not, then in the first search, what do you split this, right? You split this list. There are two sublists. One side this, and another side this. Are this list dependent?
No.
Yes or no? You said yes or no?
No.
No, right? These are completely different, right? So for instance, we cannot skip whatever part. For instance, if my value is 2, then we don't need to go this right side. We get rid of the right side, right?
Yeah.
So this is called, for instance, independent. This sublist and this sublist are independent. But here, this split, this has dependency. You see that they are using same function, same either function, or we say that it's an array over here, right? Array, same list. And this I value is dependent to this I value. Right side I value is dependent to this side I value, right?
Okay, I think I understand.
Okay, thank you. Does anyone has any other question? Some of you maybe cannot speak out. So if you have any question, please chat me, okay? Send me a chat message over here. I will see. So Justin, did you have a question? Troy? Do you have a question? Adam? Kaison? I saw Olalupa maybe over here. No, Alpha, I'm asking if you have any question. Okay, so we got basic understanding of dynamic programming, right? So dynamic programming, actually, what in dynamic programming we do, we compare with all possible solutions and then find the optimum solution. Optimum solution means either maximum or minimum. For instance, if we want to profit, then we definitely want to do maximum profit, right? So in case of profit, optimum means maximum, and in case of loss or cost, okay, so optimum means minimum value. So for cost, we will find minimum value. Okay, and compared to greedy method, for instance, some programming languages, some algorithms we discussed in our previous lectures, right? Some algorithms are greedy. For instance, in our previous week, we discussed the MST, shortest path, minimum shortest path. And in the greedy method, whatever the find, it instantly it finds the minimum value in a path, it select that one, and it start going that way. And if later it finds, oh, there is a big hole or there is a big cost, it cannot come back. Okay, compared to greedy algorithms, so dynamic algorithms sometimes actually takes time, some extra time. Okay, but dynamic algorithms give a better and optimum solution in a better efficient way, because it checks all possible solutions. Okay, so I got a slide that has actually many extra slides. So some solution, and then maybe we don't need some of these, because these are for people who for the student who do like simulation on automobile factory or electronic or electric devices. They actually implement dynamic programming like this way, but we want to focus actually something else we want to do in our next lecture. Finding sequence. Okay, find the maximum sequence, max sequence. Okay, let me see that problem. I will upload this slide. Okay, I will get rid of some.
Can you take the attendance?
Yes, some less slides from here. Okay, the top-down process is that this is called memoization, right? Memoization. Okay, it's not memorization, but okay, memoization is means holding the value. Okay, in the previous call. Okay, okay. So there are some differences. What do you want to do? Give me 1 second. We want to do okay, longest common subsequence. For instance, DNA test. How a DNA test is done to check whether two boys are siblings or not, whether a child is from this parent or not. They check the sequence in the DNA, right? So the DNA sequence, they are in the very root level. There are some symbols that check the maximum or at least minimum number of mass in the symbols. Okay, in the sequence. For instance, we are given. Give me 2 more minutes, please. This is X. This is a sequence of letter. Okay, and if we have another subsequence, for instance, this one or that one, we have to check what is the maximum common subsequence. What is the maximum common subsequence? For instance, like this. Okay, X is like this: A, B, C, D, A, B, and Y is like B, D, C, A, B, A. So we want to check sequentially what is the maximum numbers that sequentially match. For instance, this is a father DNA, and this is a child DNA, and we want to find the match. Okay, so here you see that B matches with B, and then C matches with C, and then B matches with B, A matches with A. So the maximum number of matching over here 4, right? B with B, C with C, B with B, A and N. So here maximum length, matching length is 4 over here. And then over here, B matches with B, D matches with D, and then this C does not match because whenever it passes, it cannot come back. A matches with A and B matches with B. So it has also 4 matching. Okay, so we can say that if this is a parent, this is a parent DNA, and this is one child DNA, and this is the another child DNA, then we can see that, for instance, if we have a norm that to be a child at least, for instance, 4 unit, 4 million or 4 billion, whatever you say, or 4K matching needed. So you can say that 4 matching is over here, right? So that in that case, we can say that, hey, Y is a, here, for instance, Y1, we can say Y1. Y1 is a child of X. And maybe Y2 also is a child of X. And if there is no match, for instance, then we could say, hey, no, Y2 is not a child of this parent. So for this kind of research, okay, dynamic programming is used. So this is called LCS, longest common sequence, to measure the longest common sequence. And we will see that there are some algorithms, and we will apply some of these in our next lecture. And there is another popular program, is called knapsack, 0 and 1 knapsack problem. So in a test, you will get some questions from tonight's lecture and the next lecture. Hopefully I will be able to see you in face-to-face in our next lecture. So let me get the attendance. Does anyone has any other question? Cameron, you're here, right?
Yes.
I will give attendance. Okay, no problem. Okay, maybe I'm giving you attendance in the previous lecture. Okay. I think everybody does not have a speaker, so I'm skipping attendance today. Okay.
Okay. Well, I didn't get attendance for previous lecture.
One of the lecture you are absent, so I give you. Your attendance is good. Okay. Well. Okay. Does anyone has any question? I think if you start reading dynamic programming, you will get some interest. And for advanced algorithm, if you take advanced algorithm course, then this is the starting point. This will be starting point. Then you will see that you will use you will use dynamic programming a lot. Okay, that's all for tonight. Let me see if anyone has any other question.